and ultimately started Tuesday with was looking at biochemistry, the functional groups associated within it, and what functional groups we might want to look at. So we will continually see these functional groups pop up. What's more important than knowing the name of the functional group is kind of its function, its reactivity. How can it interact with other molecules? And we will talk about that in just a second. But before we do that, it doesn't hurt to go through and start to come up with the names for the primary functional groups you'll be concerned with. So we can go ahead and identify those. We've got amines. We've got our alcohols. Where are we? Carboxylic acids. We've got what I'll reference as just our alkyls. Okay, so that includes our alkanes and our alkenes. We aren't going to delineate too much beyond those because really for the most part our alkanes and our alkenes react very similarly in biochem. They're both fairly nonpolar molecules that just don't really do a whole lot for us. I don't have this functional group John on here, but I can make an adjustment to it. This one will be kind of important. That one is, we have to be really careful with the pronunciation of this one. Okay. And depending on how you choose to pronounce it, I try and pronounce it as phenol. Okay. Whereas if we look at just the group circled in blue, that is phenol. Okay, with a YL. Okay, I know that can be confusing. Kind of watch out for that. Phenols we won't really care about. Phenols with the O will be a lot more important because we get more chemistry out of those. The ethers, the aldehydes, ketones, not quite as important. The aldehydes and ketones do still have a lot of chemistry associated with them as carbonyls, but where we're going to see those functional groups primarily show up is in our carboxylic acid. So our carboxylic acid carbonyls are driving force carbonyl substrate. Okay? Questions about any of that? There are other ones that will pop up. We'll talk about them as they show up, but for the most part, we just want to have kind of a cursory understanding of what functional groups are primarily going to be concerned with. Okay, so you should review table 1.1, which has a whole lot more to it than we really need, but it's got some information there. Biochemistry, there's really three common themes that come out of this. Okay, we get the same biomolecules that we get in organic chemistry, the same kind of functional groups that we've talked about there. And we get physical chemistry applications that come out of biochem. So it sometimes can be, or more appropriately is classified as physical chemistry, but typically where you've seen it already is in inorganic chemistry, which for some reason is actually classified as general chemistry. So the topics that were covered in Gen Chem do show up in Biochem, particularly when we look at kinetics and thermodynamics, which is really unfortunate because anybody that took 130, how much do you remember of kinetics and thermodynamics? It's never talked about in Chem 130, okay? Or if it is, it's to a very, very, very small extent. Okay? So we'll kind of gloss over the physical chemistry aspects. When it hits those chapters, those will be rough, but I'll try and zero in on just the parts that you would need, okay? Which is ultimately what a biochemist would do. They don't care about the theory, they just care how can I interpret this quickly and easily. And then we also kind of get an origin on where all this stuff comes from. So we can look at the chemistry of where these molecules are, all they exist, how they interact with each other, but then we also run into, every so often, this philosophy. Why life? Where did things start from? Why do these things interact with each other? Okay. Which really just shows up in chapter 1. After that, we kind of ignore the philosophy aspect and we stick to the chemistry aspect. So the big gap in our philosophy is how did we shift from inanimate to animate objects? Okay, and so we had to come up with theories on where we started with. Okay, so our basic understandings, we make some assumptions and we say we started with these simple molecules. You notice of those simple molecules, depending on your classification of organic, none of them are organic, okay, which is interesting. If we start with no organic materials, how do we transfer to now becoming all organic? Okay, and there were a variety of experiments and theories postulated about this. Probably the more famous one is the Miller-Urey experiment. The main reason why it was super famous, or made super famous to me, is that they were chemists at UC San Diego, which is where I did my undergrad. So every chemistry class that I ever took in San Diego had to reference them, and they have a whole hall developed to them describing how awesome their chemistry was. It is kind of an interesting theory. So they took a closed system, took all these gases and molecules and put them in there, and then just beat the crap out of them. Okay? So random sources of energy, and hoped for some heating and cooling aspects, local pockets that you might expect in a larger system, and trying to see what would come out of that. Right? And as they processed the experiment, they did start to note that they made other molecules. So they had cyanide, they had an aldehyde, they made some small amino acids. Right? Well, if we think about even making an amino acid, even a simple amino acid, is pretty shockingly amazing that they were able to do this, considering what went into this. Okay, if we go back to the theory of where life started from, we're looking at millions of years ago. Okay, and they tried to do this, and in a matter of 20 years, they actually replicated or were able to synthesize through random action some amino acids. Okay, so that's actually kind of impressive. Okay, they were even able to get amino acids out of just such a simple experiment in such a short amount of time. Okay, so it is kind of neat that that could happen on its own. Going from simple amino acids to complex structures is a whole other argument, and they've continued to run this experiment and just hoping to see more complex things come out of it. You still run into this issue of how do we scale up from that. And that is not a problem that has been solved, though I did recently see an article that there's a scientist, mathematician or physicist from one of the Ivy Leagues, I believe, that has come up with a thermodynamic explanation for why life actually makes sense to go from tiny molecules to up to larger life. And that's because all things are trying to disperse energy efficiently. Well, a random small molecule does a horrible job dispersing energy. But if you make that small molecule into, say, a chlorophyll, okay, that does a really great job of dispersing the energy. So it actually makes sense to increase the order locally, because you can increase the disorder further outside of that local environment. And he allegedly came up with the thermodynamic proof for all of this. There's no real evidence. It sounds to be pretty up in the air at this point. They've got some people that say it's really, really cool, but we don't have enough evidence to support his theory. Okay? So it's kind of a neat concept. Could be something worth looking at for presentation. Not to detract from this theory, another possibility that's come up is RNA is the front runner for origin. So amino acids are great, but those end up being proteins. Okay, so we're saying proteins are the origin of life. That was kind of their main hypothesis. There's a lot of research coming out, or a larger view, saying that maybe RNA is actually the origin of life. So instead of coming up with simple amino acids, we need to show how can they make simple nucleotides, which is a lot more difficult from just a random solution, because those structures are a lot more complex. Is that a hand? No, that's fine. So how do we shift from the philosophy to the chemistry aspect of this? Okay. Regardless of how we get to this point, we end up getting to this point. Okay? And what we're looking at is 3 main subcategories for the sections of stuff that we need for life. Okay? One of the aspects is taking our amino acids and turning them into, well, in all cases, they're all being turned into polymers. Okay? But depending on what our individual subunits are that go into these polymers, we get different sections. So if we take amino acids, we turn those into, what do amino acids become? Proteins. Okay, which, yes, is polypeptides, but proteins is typically how we would look at it. Okay, if we take individual sugar units and we combine those together. We end up with carbohydrates, which I'm just going to write as carbs. And then if we take individual nucleotides, we can end up with our genetic information. We're looking at DNA and RNA. Which is ultimately our genetics. Genetics is a whole other animal in itself, so if you want to learn something more about genetics, you need to take a genetics class. Okay, all we'll really focus on is what are the pieces that make up DNA and RNA, and then you guys or me later will do small little sections of replication, translation, all that fun stuff. Okay? So we've got those three main subcategories. So you need to be able to look at an individual structure and say, okay, what do I have? Do I have a carbohydrate? Do I have DNA? Do I have proteins? Okay, so you have to be familiar with the relative patterns of those structures. This is where knowing the functional groups can come in handy, because it can allow you to see and identify these things. How does chemistry move up to biology? Now we start to assemble these things into much larger units, and cell biology, as much fun as I had taking that class, I don't have super high opinions of. It's kind of unfortunate because there is a lot of really cool stuff in biology. What we're going to be primarily concerned about is this difference between prokaryotes and eukaryotes. Your book goes through the cellular divisions of what makes them different. What we're going to shift to when we look at our genetic information is how do those different types of cells interact, or not interact, but do their replication processes, because they have slightly different genetic makeups. They do still run through similar proteins, and they do still store similar carbohydrates. But if we look at the kind of pseudo macro scale or not super micro scale systems, we can look at overall comparisons with nuclei and some of the individual components within them. Okay? So we can go through and look at each of those comparisons. Ultimately, there isn't a whole lot I can add to that other than here are the differences. Okay, so this is something that you would just kind of have to memorize. This is one of those things where you get a test which of these exists in eukaryotes but not in prokaryotes or something like that. Okay? Prokaryotes are older. Okay? Any theories on why they might be older?
They're simpler.
They're simpler. Okay? So then it comes up to a question of where did eukaryotes come from if prokaryotes are older? Why don't we always stick with the prokaryotes? And there are varying theories that go through that. You get the endosymbiosis theory, where one prokaryotic cell developed as a parasite within another prokaryotic cell, and now we start to generate these internal compartments within the eukaryotic cell, like your chloroplasts if they were photosynthetic, or even mitochondria. Okay? So you get kind of neat theories there. It's on the biology side. Here you guys have already seen most of that. We can then scale that out even further to even more stuff that I really don't care about. To look at all the individual kingdoms and what different branches are. Okay? This is kind of reading comprehension stuff, because your textbook's just going to tell you this. So if you read through the textbook, look at those classifications, and you're kind of good to run. Okay? So you will see questions along those lines in your homework. Sometimes you'll see them show up in the exams, but for the most part, I try and skew more towards the chemistry aspect for the exams. Okay? So we get, what do we have, 5 kingdoms? 5 kingdoms and all their different classifications. Okay? So now we can shift into some of the more interesting stuff. Okay? So we can look at one of our more important biochemistry reactions. Okay, why is this reaction important? What do you guys remember from biology? Any? We're looking at ATP. And in particular, ATP is what?
Energy.
Our energy for most life as we know it. Okay, so the process of ATP going to ADP, okay, is one of the driving forces for a lot of our individual reactions that we find within individual cells. right? Or it's one of the primary sources for it. And that primary source of energy is stored in that phosphate group. So that phosphate group helps to activate individual molecules. So what we do is put a phosphate group on ADP to now generate a very high energy ATP molecule. That molecule can then go out and interact with its environment, say a protein, and transfer that phosphate across to the protein. So now what happened is that ATP drops in energy down to the ADP, but what happens to our protein? It receives energy, so it now goes up and can be activated so that it can potentially do the next step of whatever it's trying to do. Okay? So really that ATP is just transferring phosphate groups around, and it's the energy in that phosphate of how it disrupts the structure, okay, or how it actually provides direct energy to our individual structures that allows for reactions to continue. Right? So we could look at a couple different thermodynamic principles that come out of this. Okay? So we've got 4 fun questions here. Before we get into those too much, it might be helpful to know what some of these symbols are. Okay? And this would come back to Gen Chem. We're primarily looking at people that had 152 because I don't think 130 talks about either of these terms. Okay, so let's work on this together. That first one, S. S is, what was that? Entropy. Okay. Well, if I was a Chem 130 student, S means about as much to me as entropy does. So let's work on that. What is entropy? Okay, one of the common terms that comes out of this is a measure of the disorder. Disorder is kind of this vague, nebulous concept. So one of the things that I like to look at it, instead of it being disorder, it's the amount of motion. Okay? So if we go through and look at this individual reaction, and we're trying to decide what happens to the entropy, okay, or the disorder, or the amount of motion in this reaction. So with that delta, we're looking at a change. So we're comparing our products to our reactants. Okay? Within that, what happened? True? But what does that do? Okay, why is it more? Okay, more compounds. Why does that mean more disorder? Why does that mean more motion?
Release of energy.
We don't even need to look at energy.
Potential collisions.
We're looking at the amount here. Okay. If I have one molecule moving around, it can only move around so much. If I have a second molecule now moving around, do I move more or less? I move more. The more you increase the molecules, the more motion you get. Okay? This is why I think the motion aspect makes a lot more sense than the disorder. So you just add another molecule, so, well, is it more disorder or less disorder? I don't know. They're both running around doing random stuff. Okay? It's kind of confusing. But if you shift to motion, kind of simplifies the topic. So if we look at our reaction, on the reactant side, how many molecules do we have? 2. On our product side, we have 3. If we look at that change as a final minus initial, in our final state we had 3 molecules. In our initial state we had 2. What's the net result? A positive 1, which means what happened to our entropy? It went up. Okay, it increased. We have a positive value. Okay. We're not trying to quantify this. All we're trying to do is qualitatively say, did it go up or down? Is it positive or negative? Okay, and that's all I want you to do with this. The 3 minus 2 gives you some numbers that you can kind of work with because it can be kind of weird to think of up and down. Okay, so the numbers kind of help with that. Okay. What if we had a reaction that did something like this? A goes to B. What's our entropy in that case? No change. We start with 1, we end with 1. Okay. At least at this superficial level, we can't really find a big difference for our entropy, which is fine. We don't need the numbers to figure it out. We just need to know bulk what's happening. Okay? What happens when we move to, can I erase all that? What happens when we move to that next term? What is delta H? Nice of them to pick a new word. Anybody heard the history on that? Difference between enthalpy and entropy? No, they aren't last names. Anybody know which one was discovered first? Enthalpy was actually discovered first. Okay? That's where you're looking at very large changes in energy. So that one's actually easier to determine. This whole disorder concept is very hard to grasp. Okay? And at least according to Wikipedia, when I last looked at it so long ago, the person that discovered entropy looked at this concept or came up with this concept of our, however you want to look at it, motion or disorder, and said this is really, really important and everybody's ignoring it. So they made the conscious decision to make the word sound the same as the other one. Because now people will get them confused and you can't forget it. Okay? Pretty obnoxious, but that is allegedly the history behind it. Okay? If it's not true, it's at least interesting enough to keep spreading. Okay? So, enthalpy. What is enthalpy? Okay? Energy is a good way to look at it. It's even more fun because we have enthalpy with an E, entropy with an E, and now energy with an E. Okay? But it's not quite just energy. Okay? It's really the energy of bonds. Okay? Are bonds making or breaking? Okay? And that's where we see the largest differences in energy, because we're making or breaking bonds. Entropy, we're looking at motion, okay, which we can kind of quantify, but it's not as easy to quantify across a reaction. If we break a bond in a reaction, we can see a massive release or absorption of energy. Okay? So the enthalpy is relatively easy to pick out and determine as long as we're under controlled systems. Okay? So that's the raw energy difference between these. Okay? If we look at this reaction, can we determine what the change was in the enthalpy? It's a little bit harder. With the reaction on its own, probably not. Okay, you need to bring in some extra information. That extra information would be potentially what bonds were being broken, what bonds were being made. So you can look up tables of those and get numbers and all that fun jazz and come up with is it positive or negative. Okay, that's a lot of work. Is there something else that we could use in this case? Do we know something about this reaction?
Lost a phosphate, you can do a double bond.
Okay, so that's getting back to the terms, okay, or breaking the bonds, but if you don't know the energy of the bonds, that doesn't work. We could use a thermometer, but that runs a reaction.
Can you go back to the fact that the entropy was +1, positive can?
No, we can't. There isn't a direct tie between the entropy and the enthalpy, unfortunately.
Groups?
No, it's even easier than that. We actually started talking about this. Which was higher in energy? ATP or ADP? ATP was higher in energy. So let's give it a random energy. Let's say it's 100. What's the energy of our ADP?
Less than.
1. It's lower, right? So if we look at our change in energy across the reaction, final minus initial. Oops, yes, sorry, that did work. Final being 1, initial being 100, what do we get? A negative. So energy was released by this reaction. Does that make sense? What was the whole point of ATP? To transfer energy to something else. Energy should be released in the course of this reaction. Okay. Do we need to know how much? For the sake of this class, no. That's not that important. If we were getting into potentially MCAT stuff, then you got to kind of watch out for that, because I think the MCAT starts to ask about the exact energies, and when you look at the Krebs cycle and glycolysis and all that fun stuff, how much energy is released by each of those things and how many ATPs go through it, they do start to get pretty nitpicky with that. Unfortunately, those areas are highly up for debate. Okay? So you really have to be careful with quantifying each of those. And since everybody's potentially taking different tests, I'm not going to force you to look at that. What I will ask you to do is that when you go through and take those tests, make sure you look up what they're asking you to have memorized. If they tell you you generate 32 ATP, you generate 32 ATP. Doesn't matter if that's wrong, that's what they are telling you to memorize. You have to memorize it that way. Okay? Same deal with the energy released or transferred. If they tell you that it's 1.2 kilojoules of energy, regardless of whether there's a reference that says that's wrong, that's what they're telling you it is. You have to accept it as what it is. Yeah.
I didn't know what the MCAT was, but.
Oh, it's the medical school test. I know there's a few students taking the MCAT. I don't know enough about, because I think there's a lot more students looking at PA school. I don't know anything about their test, unfortunately. So if anybody goes through and takes their test, you should let me know. That'd be nice. Oh, you just need a GRE? Oh, that's not too bad. You don't need to know that number then. Okay.
Later you have to take the PANCE test.
The what?
PANCE.
Yeah, at the end.
Oh.
Then you have to pass that with
Well,
colors.
you can learn it then.
Learn it then.
So remember, again, the scope of this course is to set you up for when you have to take a real class in biochemistry, a quote-unquote real class, unfortunately. I don't think I want to erase everything, but we'll erase some of those numbers, get that out of the way. So for this reaction, we said our delta S was what? It was positive, because it was 3 minus 2. Our delta H was negative. Okay? We can then throw in some extra terms. Exothermic. This could be a bit scary, but I'm hoping it's not. How many people remember what exothermic meant? Okay.
It's releasing it.
It's a release of energy, which mathematically means
It's negative.
it's a negative delta H. That negative symbol merely means release. The number is how much energy was involved. Okay? So we can run into all sorts of English issues with crossing over between mathematics and exothermic, or energy released or energy absorbed, and all that fun jazz. Okay? So you do have to watch out for your symbols. But exothermic really just means negative. So in this case, we could say this reaction was exothermic. For some unknown reason to me, and I'm pretty sure this is selective to biochemists, we bring in this extra term, exergonic. Why? I don't know. Still haven't figured that out yet. Here's another term. Exergonic means the same thing as exothermic. So if you remember the exo being the release, you should be good with that, okay, and being our negative. Whoops, and release. If we look at endothermic, it's now the opposite. So it would be an absorption of energy. It's a positive delta H. And we run into the same issue we run with endergonic, okay, being the reference in biochem lingo. Okay? For this reaction, let's say there were 52 kilojoules involved. That seems kind of high, but let's just say that's what it was. Okay. Where would I write those 52 kilojoules in that reaction? It's kind of an odd idea. It's on the product side. Okay? There's our 52 kilojoules. Because our energy was released. Well, where are things released? Products. Okay? If it was an endothermic reaction, where would I put the heat? On the reactant side, because it needed to absorb that energy to go to making products. Okay? So it's a frame of reference around the reaction equation. Okay? To be even more fun, I meant to review this because I always get it backwards. Biochemistry brings in two more terms, catabolism and anabolism, okay, which hopefully I can say consistently correct. Okay? What do those two more terms mean?
Yeah.
Catabolism was breaking, right?
Yes.
Anabolism was building.
Anabolism is building.
Is it though?
I'm
Because Ann is without in medical terminology.
one thing that I've learned to accept when it comes to biochemistry is there is no sense in naming. It is too broad of a field. There's too many been random discoveries, and nobody has sat down and said, stop naming it nonsensically. You have to name it according to some rules. So if you thought nomenclature was a challenge in organic chemistry, you don't even want to attempt to think about how things are named in biochem, because it goes all over the map. Okay. Very, very inconsistent. So what does that mean with our enthalpies? If we're breaking, what would we expect for our enthalpy? Okay. It's going to be a release of energy. So it'll be negative. If we're looking at anabolism where we're building it, it's absorbing that energy, it's becoming positive. Okay, so anabolism is a way to store our energy. Catabolism is the way to release that energy so we can use it. Okay? So this is fun. What's the delta H, positive or negative, for the reaction shown?
Negative.
I got obnoxious. I swapped it on you. So not, okay, so there's an interesting point. Let's look in the
There's the
reaction,
overall reaction.
not the energy diagram. Ignore the energy diagram for the moment. Okay. If we look at that reaction, what's our delta H? Positive, you're making ATP. You're going to the higher energy state. To get to the higher energy state, what do you have to do? You have to give it a source of energy. Okay, so our energy in this case is going to be on the reactant side so that we can make our ATP. What happens to our delta S? It's going to be negative. Okay, so our disorder goes down. We have less motion because we're moving from 3 particles to 2. Okay? Would this be catabolism or C or the A?
Anabolism.
It's anabolism because we're putting energy in to make this higher energy molecule. Okay? If we now kind of scale out and ignore the overall reaction, we can look at energy diagrams and try and predict what's going on within these energy diagrams. Okay? This is a figure that if you've had me, you have almost undoubtedly seen because I show it in, I think, every single class I've ever taught. Okay? And that's because it's really, really important. What we're looking at is an energy diagram where all of this information is somehow stored for us. So we've got our reactants, okay, at some energy level. Okay? We've got our products at some energy level. Okay? And if we're going to look at a reaction, we have to somehow get from the reactants to the products. And there's 2 things that control that. Okay? We've got the raw energy difference and transferring between our reactants and products. Okay? And we saw an energy difference before. That was primarily our enthalpy, our delta H. But is delta S also an energy term?
Yes.
Yeah, so it needs to also be involved somehow in our reaction. Okay? So what we're looking at is the combination of our enthalpy and our entropy that makes the energy difference in an energy diagram. That energy difference is referred to as the Gibbs free energy. Of course, yet another symbol. That's our delta G. In most circumstances, the contribution from the entropy is so small that it becomes negligible, which means our delta G ends up equaling our enthalpy. Okay? So some of that may come from remembering the relationship between delta G and delta H and delta S. It's delta H minus T delta S equaling to delta G. Because delta S entropy and enthalpy are independent terms of each other. Okay, so they are going to contribute differently. You'll also notice that if we ignore one term over the other, we can start to build preferences in what we would expect for a reaction to occur. Okay, and we'll look at that in just a second as well. So on this energy diagram, we've got this energy contribution. But that's not the only thing that helps us out, because there's our thermodynamics. It's the raw energy difference between our reactants and products. Okay? And if we had this energy difference where our energy goes down, that's a good thing. That's favorable. Okay? But what if I told you that the reactant here is humans and the product here is CO2? That's an exceptionally exothermic reaction. Why is that a bit problematic if we just look at the thermodynamics? Do we exist? If that reaction is so thermodynamically favored to go from humans to CO2, why do we exist at all? Why aren't we all just a giant ball of CO2? Okay. There's some other contribution to this. What is that contribution? How fast does the reaction occur? Not just can the reaction occur, is it favored to occur, but how fast does it occur? That speed has to do with the upper half of this curve. That's the kinetic aspect. And the kinetics are dependent on this transition state. How high of a barrier to the reaction is there? What is that barrier typically referred to as? The activation energy. Thankfully, the activation energy to turn us into CO2 is really, really high. So our standard kind of walking around and living our everyday lives isn't so bad. Okay? We don't spontaneously combust because we have this massive activation barrier. Okay? We need a lot of energy to be input to convert us from our reactants to get over that barrier to turn into CO2. Okay? So we have to realize that we have these two subcategories of things that determine how well and how efficiently our reaction occurs. And when we look at organic chemistry or even general chemistry where we're just taking test tubes and mixing stuff, okay, in those circumstances we have to be super aware of what's happening both on the kinetic side and the thermodynamic side. Biochemistry skirts this entire issue because what do we do in biochemistry? We use a cell or a protein that has been evolved for millions of years to do that reaction. So we don't have to worry about the kinetics and thermodynamics because something else did it for us. Right? Which is why I don't like biochemistry. Because you want to do something in biochemistry, you find a cell, tell the cell to do it, the cell does it for you. Oh, look at what I did. You didn't do crap. You told the cell to do it for you. Okay? It's a bit pessimistic. Okay, but that's one of the issues that I have with biochem. There's very little kind of thought. You just make something do it for you. Okay? So within this, we talked about delta S, we talked about delta H, and we've now brought in this term of delta G, okay, our Gibbs free energy. And we want to think about now what's going to be a favorable situation. So if we look at just the thermodynamic aspect, what's going to make this reaction likely to occur? Well, one of the things we just mentioned is that energy always needs to decrease. We're trying to go to a lower energy state. Okay? This is true because you stick your finger in an electrical outlet, what happens? A lot of energy runs through you. It's usually a bad thing. It's because that's at a very high energy state. And what are those high energy electrons trying to do? Go down, get to a lower energy state. So when we look at our Gibbs free energy, we're always trying to transfer down to a lower energy state. Always. And this is going to happen in biochem, every chemistry. We're always trying to transfer down to a lower energy state. Okay? So what would our delta G be for a favored reaction? Okay? Remember, we're looking at the difference between our product energy and our reactant energy. Well, if the product energy is lower than our reactant, again, we can pick some random numbers. There's 1. Our reactant will say it has a higher value. 1 minus 100, negative. So our favored state, let's go ahead and use a different color here. Our favored state for our delta G will be negative. Okay. Favored makes too much sense. Okay. So instead of calling it favored, chemists in general have come up with the term. Anybody? Spontaneous. Remember, this says nothing about speed, so that makes this even more weird. Right? When we think of spontaneous combustion, we think, oh, boom, somebody just lit up on fire. Right? It just randomly, quickly, really quickly happened. Spontaneous does not mean that in chemistry. Spontaneous means that the reaction can occur. It says nothing about how fast. Right? If we now shift over to the other side of the equation. We want to think about what things over here are going to help us get to a negative delta G, or a spontaneous reaction. Right? I'm going to ignore delta S for the moment, because I think delta S is confusing, because I got to multiply it by something else, and I even got to bring in a minus sign. I don't want to deal with that. Okay? So let's ignore delta S for the moment. If we look at delta H, what would be a favored delta H? Why does it need to be negative? Delta G needs to be negative. We have to move to that lower energy state. So our favored state for delta H will be negative. If delta H is negative, is it spontaneous? Sometimes. Okay. The spontaneous term really, unfortunately, only applies to delta G. Favored can apply to everything else. Delta G, delta S, and delta H. Right? Now let's ignore delta H. I don't want to look at that. Now I have to bring in the harder one of our minus T delta S. What sign do I want on delta S to make delta G negative? Okay, how is a positive equal to a negative? You got to be careful with your mathematics. You got a negative sign in front. Doesn't the temperature affect it? I can have negative temperatures. Why does the temperature not affect it? We don't have negative temperatures, because our temperature scale we use for this, Kelvin. Okay? Kelvin is 0 upwards, always greater than 0. Yes. Okay, so we never have a negative temperature, which means our favored delta S is positive, which is interesting because that brings up, what is it, the second law of thermodynamics? What happens for entropy? It's always increasing. There's always an increasing disorder in the universe. And that comes back to trying to decrease the overall energy. Try to get that favorable reaction. Okay? Kind of makes sense? Okay. So, always fun to bring this up. So when we mentioned that whole delta H being negative, does that mean it's always a spontaneous reaction? Remember? Favored, yes. That does not mean the reaction is spontaneous. The spontaneous term only applies to our delta G's. Okay? So we would have to go through and look at all of the possible permutations of this. So this was pulled out of, I think, my 152 lectures, a nice little table that summarizes all of those results. Okay? This is something that you should be able to derive just like what we went through and did with a negative delta G. But what if I want a non-spontaneous reaction? Delta G needs to be positive. What has to happen to delta H and delta S to get that positive value? Okay? We've got a couple different options. To guarantee it doesn't work, our delta S needs to be negative and our delta H needs to be positive. Okay? So this table summarizes that all nicely for you. Okay? You should practice and go through and make sure that you can do it all appropriately and kind of derive those results. If not, it may make the homework a little bit more challenging, or you just memorize this. This is unfortunately one of those things. You can just memorize it and you can get away with it for the first exam. Okay? Questions about that?
So we should just concern ourselves with delta H, S, and then
Delta G.
T always has to be positive. Anyway.
T will always be positive. So yeah, I don't like this table because it gives you this. Actually, I can do it this way. Because it gives you that extra little term in there, which to me, when I looked at a positive, positive, negative, wait, what's going on? That extra term was kind of confusing to me. But I haven't had time to build my own table. Okay? Questions about that? I believe that is chapter 1. Yep, that was chapter 1. So now what we're going to do is move into chapter 2. In pretty much every textbook I've seen, they seem to have a chapter or multiple sections on how awesome water is. Okay? I kind of understand that. It's particularly important for biochemistry because we're looking at the science of life, and as far as we know, life is all centered around water. So water is our bulk solvent that surrounds everything that's going to happen with our proteins, with our genetic material, and with our carbohydrates. Okay? So water is really important to go through and understand its different aspects and what it can do for us or against us. And yes, the against is actually a helpful tool. Okay? So if we go through and look at the structure of water, which I'm pretty sure I was supposed to find a nice image of water, we've got H2O. I'm probably not going to make you draw Lewis structures on the test, so it shouldn't be an issue. If you've got questions on how I came up with the structure for water, just talk to me after class and make sure you're tied up for that. Things that we should already know about it. We have polar covalent bonds. Okay, that can be a bit dicey. How many types of bonds do we have? There's polar covalent, there's non-polar covalent, there's an ionic bond as well. And we will look at a breakdown of all of these bonds and forces in a second. So we need to be able to classify between each of those. So how do we know we have a polar covalent bond versus an ionic versus non-polar covalent? As a rough approximation, opposite sides does work, but it's more appropriate to look at the electronegativities. Okay? Because if we push this further to, say, sodium chloride, if we look at them, they are immediately opposite sides of the periodic table. But the bond in sodium chloride is ionic, okay, not polar covalent. And the reason being has to do with the difference in electronegativity. Okay, so you can go through and use your strict definitions on that. I believe ionic is something greater than 1.7 as a difference in electronegativity. Polar covalent is anything now greater than 0.5. Depending on who you talk to, that number changes. So I don't like looking at the electronegativities. Instead, I like looking at ionic bonds being a bond between metal, non-metal. Polar covalent, I think, is too hard of a definition to memorize, so I don't memorize it. I memorize non-polar covalent. What's non-polar covalent? Anything with the exact same electronegativities, because then your difference in electronegativity is by definition going to be less than 0.5. Okay? There is one additional thing that you have to memorize as a non-polar covalent bond. What bond is that? Carbon to hydrogen is a non-polar covalent bond. Okay? The difference in electronegativity there, I think, sits at like 0.4. Okay? Maybe, no, actually, I think it's lower than that. Okay? It's less than 0.5. Stick with that. Okay? So water, polar covalent bond. With these polar covalent bonds, that ends up generating really large dipoles within the structure. So with the oxygen being so much more electronegative than hydrogen, it picks up a partial negative charge. And the hydrogen picks up partial positive. And this happens on the other side of the molecule as well, to the point that what we end up with, we summarize this all together. Glad I wrote it all out and now erased it all. That's fun. We end up with a really large partial negative at one end and a really large partial positive at the other end. Well, one of the things we said we were striving for is low energy. Well, what is charge? Low energy or high energy? Really high energy. So what we've now generated is a molecule that has charge associated with it. That charge needs to be stabilized. So what does it do? It does anything it can to stabilize that charge. How do you stabilize a positive charge? Put it near a negative atom. Okay? Like another oxygen molecule from another water molecule. That new interaction between those two molecules gives us hydrogen bonding. Right? So in this figure, where is the hydrogen bonding shown? Trick question. It's not there. We need a second molecule.
It's got to be intermolecular.
Inter is within the molecule. Intra is outside.
Yeah, it's the other way around. Intra is within, inter is outside.
You're right. It's intermolecular forces. You're right.
That it makes sense.
You're right.
The naming.
Well, that's because that was chemistry, not biochemistry. So what we get now is a hydrogen bonding interaction between the hydrogen and the oxygen. How many different hydrogen bonding interactions can water generate for us? Well, over both of these hydrogens can hydrogen bond. Okay, so that is 2. If this is a hydrogen bond, is this oxygen not contributing to it? Yeah, it is. What's contributing to it from the oxygen? Which electrons?
The lone pair.
The lone pair electrons. So if I look at an individual water molecule, each hydrogen can act as a hydrogen bond donor because it has a hydrogen to donate out. But what does the oxygen do? It acts as a hydrogen bond acceptor. How many lone pairs are on the oxygen? 2, which means it can potentially connect up 2 more. So an individual water molecule has the potential for 4 hydrogen bonding interactions. Okay? Which is really weird, but that's how your homework counts it as well. So I want to make sure you're aware of that. Okay? So other things that contribute to this. We generate these large partial charges, which is why we get hydrogen bonding. That's the main reason. Okay? The next part is that it's relatively small. So if we based our life on a very large molecule, everything else would have to scale up to be a larger molecule as well, because this molecule needs to get in and dissolve things and interact within other structures. So the small size actually contributes to this. The other thing that's nice with water is it has multiple symmetries, which is mentioned in your textbook, and then they just kind of ignore for the rest of the textbook. Okay? But multiple symmetries mean the orientation of the water molecule doesn't matter that much. Okay? So if I orient the molecule with my fist on this side, I can get a hydrogen bonding interaction. But if I turn the molecule around, I can still get a hydrogen bonding interaction. So those multiple symmetries allow for more interactions. We don't limit the possible orientations. We've got a lot of possible orientations that allow us to do those interactions. All right, so those are kind of the neat things. So within this, our hydrogen bond donor and our hydrogen bond acceptor. Our hydrogen bond donor will have to have a hydrogen. Okay, but for it to be a hydrogen bond, that hydrogen needs to be very, very, very positive. How does the hydrogen become positive? It has to be bound to an electronegative element. So whatever's over here has to be electronegative enough to take electrons in that bond away from the hydrogen, making the hydrogen positive. So what elements are electronegative enough? Fluorine, oxygen, and nitrogen. I don't know why my pen keeps spinning on me. Okay, so we have to have that to generate a hydrogen bond. The hydrogen bond acceptor, okay, needs to be something that has a large partial negative. So that when we look at the hydrogen bond between these, I'm looking at the interaction between a large partial positive from our hydrogen and a large partial negative. Well, what's going to generate a large partial negative? Elements that are highly electronegative, such as fluorine, oxygen, and nitrogen. Okay. Do I care what they're bound to? We can definitely run into some gray areas here. As long as they are not bound to fluorine, oxygen, or nitrogen, we will have generated a strong enough dipole to get our hydrogen bonding interaction. So what they're bound to isn't all that big of a deal, as long as it's not fluorine, oxygen, or nitrogen. Okay? So we have to be careful with that, not to give away too many answers here. But let's take a look at the molecule of, actually let's just erase everything. I take HF. Hydrogen bonding or not? Yeah. I have the hydrogen bond donor here, and I have the acceptor over here. That fluorine is bound to a very low electronegative element. How about now? Yeah. How about now? Remember, our acceptor, our hydrogen bond acceptor, it's still an acceptor here, okay, is bound to anything that is not fluorine, oxygen, or nitrogen. Okay? That oxygen does count as an electron donor. Okay? Is it as strong of a hydrogen bonding interaction? That's a different argument. Okay? You're right, it's not as strong of a hydrogen bonding interaction, but it still fits the definition. Still fits the definition. Is it a strong one? No. It gets progressively weaker. Our acceptor absolutely satisfies our definition. Does the donor? No. The hydrogen must be bound to nitrogen, oxygen, or fluorine. It's not one of those elements. This is not a hydrogen bond.
And that's because it's not going to generate a partial charge.
It doesn't generate the partial charge. Okay, so what we went through and did with this is we ended up kind of skipping over our definition of hydrogen bonding. Okay? Hydrogen bonding on its own, as we kind of danced our way through it, we provided examples of what works for them. But hydrogen bonding is specified by two special categories. One we did very clearly address. For hydrogen bonding to be true, we have to have a hydrogen bound to nitrogen, oxygen, or fluorine. What's the first thing that has to be true?
Partial charge.
Yes, but we can get a little bit more specific than a partial charge. No, that's a rule too.
Okay.
So it definitely is there, but there's another thing that shows up. Arguably, there are three types of bonds, and there are three types of forces. If we take a look at our force side of this wheel, how many forces do we have? 4. What's the one that's... No. What's the one that really isn't a primary force? Hydrogen bonding. For us to have hydrogen bonding, rule number 1, there must be a dipole-dipole. Without the dipole-dipole, it doesn't matter if hydrogen is bound to nitrogen, oxygen, or fluorine. What this dipole-dipole means is that we have two molecules. Each of those two molecules has a dipole. So if molecule 1 has a dipole and molecule 2 has a dipole, what's the interaction between them? Dipole-dipole, really creative. Okay? So if we look at our forces, we really have 3 categories: London dispersion, dipole-dipole, and ionic. Why does hydrogen bonding get its own special term and always gets included as its own force? Because it is so important, because water is all of life. Right? That is why it gets its own name, and only because of that. Right? Really, all it is a special case of the dipole-dipole force. Okay? So, let's get into the, or actually questions.
Could the acceptor be like nitrogen bound to a fluorine then? Would that be like a smaller?
I think that technically fits under the definition. Yep. You won't see definition, or you won't see that show up, but it does technically fit that definition. I believe the issue you're going to run into is if you built that bond and you put it near a hydrogen that would act as a hydrogen bond donor, it would react, and immediately you wouldn't have that molecule anymore. So it wouldn't be hydrogen bonding, but it would be a strong enough interaction to cause a reaction to occur, and you won't be looking at that point. Does that make sense? So this chart is one of my favorite charts, and not, well, it is kind of just because I made it. But I think it helps outline the differences and the similarities between our bonds and our forces. Okay? So what we're looking at on the left side of this are all our 3 possible types of bonds, and we just real quickly address those definitions. Okay? Covalent or nonpolar covalent, I tend to leave off the nonpolar part. It means we had an atom bound to something with a similar electronegativity, which means what charge is generated on a molecule that's purely covalent? No charge. Does it want to interact with another molecule then? Why not? There's no reason to. Absolutely no reason, because it's neutral. So what type of interaction would we expect for it interacting with that other molecule? Would it be a strong one or a weak one? Incredibly weak. There's no reason for it to build that attraction. There's our London dispersion force. London dispersion happens to be the weakest force. Why is it the weakest? Because it's coming from a structure that is purely covalently bound, which has no dipole, which means there's no reason for it to interact. We get weak forces. So if I have a bond that I classify as, say, let's pick a color I can see, purple, a purple covalent bond, that's going to result in what type of force? A purple London dispersion force. Okay? And it will scale accordingly, because if I have a black covalent bond, meaning complete equal sharing of electrons, there's absolutely no reason to interact. The interaction there is going to be an even weaker London dispersion. So when we think of these things, typically when we get taught these, we have these bonds. They're very black and white. Covalent bond is complete equal sharing of electrons. Ionic bond is a metal and a nonmetal. Okay, that's really a load of crap. It's a spectrum, okay, just like a rainbow. And that's what I'm trying to show here. We've arbitrarily decided that our cutoff, going from covalent to polar covalent, was a difference in electronegativity. Could we have changed that to something else? Absolutely. Are there exceptions? Absolutely. But that's where we decided to build that cutoff. Just like when we look at the rainbow. Okay? You look at a rainbow, do you see mauve? I don't know what color mauve is. What color is mauve?
Purpley red.
Purpley red. There we go. Good. That is in there. That should be in our rainbow. Because what colors are in the rainbow? Every color. But when we talk about what colors in the rainbow, what colors do we get? Red, orange, yellow, green, blue, indigo, violet. Mauve isn't there. Oh, why is it not there? Because we arbitrarily said that those were the seven? Some number of colors in our rainbow. Okay? We're doing the same thing with our bonds. And we're doing the same thing with our forces. Ultimately, what we have here is a continuous spectrum from sharing of electrons between two atoms, an incredibly strong attraction. Then as we start to pull those atoms away from each other and look at the changing attraction, we say, well, now that's a polar covalent bond. Still a bond. We start to pull those a little bit further apart, and the electrons are now jumping to one atom over the other. Now we're saying it's an ionic bond. As we start to pull them a little bit further apart, we say, it's not really a bond anymore. It's kind of a force. It's not quite strong enough to be classified as a bond. So now we call it a force. We pull them further apart. Okay? Now they aren't an ionic force. They're a slightly weaker force. It's a slightly weaker attraction. Until we get all the way to the London dispersion where we say there's virtually no attraction. So this whole system is really a rainbow all the way through, from purple all the way out to red. But if we color it that way, it doesn't make as much sense to me, because if we look at a polar covalent bond, what are the forces possible to it? Green. We're definitely in the dipole-dipole range. Can we be hydrogen bonding? Sure. What do we need to satisfy? The extra rules. Okay? So that's kind of the idea of this, is seeing this spectrum, which means if we go, that's probably a bad idea to go all the way back to the functional groups. When you look at a functional group, this is what you should be thinking about. What forces come from that molecule? Because it's those forces that are going to determine how proteins fold, how DNA spirals into its double helix. It's all about those forces and which of them generate stronger or weaker attractions. Okay? And I'm